In this lecture, we're going to revisit the knapsack problem and elucidate the idea of stage and state. Sometimes the idea of stage and state helps us when formulating how we're going to actually compute a dynamic program. In this case, we're going to look at the recursion. Here we're looking at the optimal knapsack value for a particular set of items, the items up to I, at a particular capacity, capacity lambda. And we note that to do this, we need to compute the value for two subproblems. We need to compute the value for the subproblem up to I minus 1 with a smaller capacity, and we need to compute the value for items up to I minus 1 with the same capacity, with capacity lambda. We're going to assume that the size of our item is going to be equal to 2. When we do this, we can identify where our subproblem is in terms of a matrix. And we can also identify which subproblems are required in order to compute this subproblem. In this way, here we've organized all of our subproblems into a matrix. And what we've done is created some dependence relationships through our recursion between the subproblems. In this case, the fuchsia subproblem depends on the blue subproblem as well as the green subproblem. And so we have to be sure that we compute both the blue subproblem and the green subproblem before we compute the fuchsia subproblem. There's a lot of different orderings that can accomplish this, and the one that we showed in the previous lecture is one of them. First, we order the items arbitrarily, and then for every item, we're going to compute the value of the knapsack up to a capacity from 0 to capacity capital C. This matrix that we have should really be considered the computation matrix. And for any dynamic program, writing the computation matrix is going to be a useful tool. It can tell us the order in which we have to compute all of the subproblems. A handy way to think about this computation matrix is that there's one primary dimension and then a bunch of other secondary dimensions. This primary dimension is something we call the stage. And in our case, the stage is the item. We iterate through the items and then we compute for every item the capacity from 0 up to capital C. In this case, our capacity is going to be our state. The state is something that's computed at every stage. Breaking a dynamic program up into this idea of stage versus state can sometimes be handy when we're actually thinking about the computational structure. The computational matrix is essential for very high dimensional problems. In this case, it's just useful for the two-dimensional problem. We could have done it without it, but it is a useful tool. We can also apply the idea of the computational matrix to a one-dimensional problem. Recall that in the shortest path problem, our subproblem was looking at the shortest path from S to I. When we did this, there's only one dimension to our subproblem, the index I. If we look at a particular node I, we can identify the subproblems. In this case, we have a node I in fuchsia, and the subproblems we have to compute are here in blue. In this case, our matrix is really just a vector, and we have to be sure that as we move along this vector, anytime we compute a particular value of this vector, that all the values previously have been computed. This is why we did a topological sort in the shortest path case. Separating the computation into stage and state and configuring it inside of a computational matrix is going to be very helpful when we think about implementing a dynamic program. But we should be careful about dimensions. Dimensions are inherently a bad thing. To see why, suppose that we have m dimensions. For dimension I, suppose that there's di possible values that dimension can take, di discrete values. Then the running time of our dynamic program is going to be the multiplication of all these values from 1 to m. This can potentially be a huge number, and so our running time can potentially grow very large. In general, if we have a dynamic program with a smaller dimension, we prefer it to a dynamic program with a higher dimension.